Welcome to Lecture 3. This week we will continue talking about inverses of matrices. I'm going to start by talking about an algorithm for finding the inverse of a square matrix of any size. We'll talk about an important theorem called the invertible matrix theorem. We'll talk about diagonal matrices, triangular matrices, and symmetric matrices. And then I'm going to finish by talking about some applications of linear algebra. First, let's go through how we can find the inverse of any matrix. Let me start by reminding you, a square matrix A is called invertible if there exists a matrix A inverse of the same size such that these two equations are satisfied. A multiplied by A inverse is the identity matrix, and A inverse A is equal to the identity matrix as well. A matrix which is not invertible is called singular. Before we can get to the algorithm, we need to talk about elementary matrices. An elementary matrix is one that is obtained by performing a single elementary row operation on I. So, for example, if we start with the 3 by 3 identity matrix, and if we do one of the elementary row operations, let's say we do minus 3 times row 1 plus row 3 gives us a new row 3. Because we've only done one elementary row operation, we have an elementary matrix. Or go back to the identity matrix again, we could do a different elementary row operation. I could swap row 1 with row 2. Or I could multiply a row by a number, and that would also give me an elementary matrix. Now, elementary matrix means we're just one elementary row operation away from the identity matrix. If we did a second elementary row operation, then we get to a matrix which is not an elementary matrix. Elementary matrix means we can only do one elementary row operation on I. Let E1, E2, and E3 be these 3 elementary row operations. That's the 3 which I did earlier. I'm getting to talking about inverses. Let's suppose A is a general 3 by 3 matrix. Let's say it's the matrix A, B, C, D, E, F, G, H, I. Calculate E1A, E2A, and E3A. I'm going to leave it for you to check these. It's just multiplying 2 matrices together. Let's look at the first one, E1A. Note that if we start with the identity matrix and we do the row operation minus 4 row 1 plus row 3 goes to the new row 3, we get E1. Or if we start with A and we do exactly the same elementary row operation, that's minus 4 row 1 plus row 3 goes to row 3, then we get E1A. And I'll leave it for you to check that if we do the row operation swapping row 1 and row 2, on I, we get E2. But if we do exactly the same row operation on A, then we get E2A. If we do the row operation 5 times row 3 on I, we get E3. If we do exactly the same row operation on A, then we get E3A. So in fact, multiplying a matrix on the left by an elementary matrix is effectively the same as doing the equivalent elementary row operation on that matrix. But remember, all of these elementary row operations are reversible. Swap 2 rows, swap them again, you're back to where you started from. Multiply a row by 5 and then multiply it by a fifth, you're back to where you started from. That means every elementary matrix is invertible. And elementary matrices are important for this field. An n by n matrix A is invertible if and only if A is row equivalent to In. And if A is invertible, then any sequence of elementary row operations that reduces A to En, or if we multiply on the A on the left by any collection of elementary matrices, this process also transforms the identity into A inverse. The proof of this theorem's in your book. I don't want to go through the theorem, but because of this theorem, we have our algorithm. The first thing we're going to do, step one, if we're trying to find the inverse of A, is we're going to glue A and I together side by side to form the augmented matrix where A is on the left and I is on the right. Step two, we're going to use Gauss-Jordan elimination to reduce this augmented matrix to reduced row echelon form. And then by the theorem, if A is invertible, then what we're going to obtain is an augmented matrix with I on the left and A inverse on the right. If we don't get this, then we know that A is singular. Let's do an example. Find the inverse of the matrix 0, 1, 2, 1, 0, 3, 4, minus 3, 8, if it exists. So step one, we're going to glue this matrix together with the identity matrix. We're going to have A on the left and we're going to have the identity matrix on the right. A is a 3 by 3 matrix, so our augmented matrix is going to be a 3 by 6 matrix. And then we're going to row reduce this matrix to reduced row echelon form. Here's the calculation. I'm not going to spend time talking about this. I'll leave this for you to check later. After we've reduced this, our AI reduces to a matrix with the identity on the left and then another matrix on the right. And this matrix on the right must be A inverse by the theorem. So then we can just read it off. Because the matrix AI is row equivalent to the matrix I A inverse must be this orange matrix, minus 9 over 2, 7, minus 3 over 2, minus 2, 4, minus 1, 3 over 2, minus 2.5. Let's just check this. We could check this by multiplying these two matrices together, and I leave this for you to check. Check that if you multiply these two matrices together, you do get the identity matrix. Another example. Does this matrix have an inverse? Well, let's try our algorithm again. We'll put A on the left and the identity on the right, and then we're going to row reduce and see what we get. Now, the problem is these 3 zeros, which I've written in red. Because we got 3 zeros here, it's not possible to get the identity matrix on the left. It's not possible to row reduce A to I. That means A does not have an inverse. That means that A is a singular. Find the inverse of the matrix 1 minus 2, 2, 4 by using this algorithm. So we do the same thing. We start with our matrix A and we write that on the left, and we write the identity matrix on the right, A on the left, identity matrix on the right, and then we row reduce this. And we keep going until we have I on the left, and then the matrix on the right, the 2 by 2 matrix in this example, must be A inverse. So then we can read off A inverse is a half, a quarter, minus a quarter, 1/8. Now, let's suppose that EJ denotes the jth column of the identity matrix, IN. So EJ is the vector 0, 0, 0, 1, where 1 is in the jth entry, and then 0, 0, 0, 0. We can think of the row reduction of AI to IA inverse as simultaneously solving these n equations. AX is E1, AX is E2, AX is En, etc., using the ideas from the first lecture. Indeed, if xj is the solution of AX equal to EJ, then A inverse must be first column x1, second column x2, and so on. Now, this is useful because sometimes we only need to find the elements in one of the columns of A inverse. If we only want to find the jth column of A inverse, we don't need to find all of A inverse. Instead, we could just row reduce the augmented matrix A EJ. For example, find the second column of the inverse of 2, 3, 1, 4. Now, before I start that, we have a formula for inverses of 2 by 2 matrices. Using this formula, we could find A inverse, and then we can see that the answer to this question should be minus 3/5, 2/5. But I don't want to solve the question like this. I want to solve it using the algorithm. What I want to do is I want to row reduce 2, 3, 0, 1, 4, 1, because 0, 1 is the second column of the identity matrix. After we row reduce this, we will find the second column of A inverse. So here's the calculation. And we do find this. We do find minus 3/5, 2/5. And this matches with the previous answer. The second column of A inverse is the vector minus 3/5, 2/5. Next, I want to talk about a famous theorem called the invertible matrix theorem. We're going to suppose that A is a square n by n matrix. Then the following statements are equivalent. That means for a particular matrix A, either all of these statements are true or they're all false. Or to say it another way, if you have a matrix A and you know that one of these statements is true, then you know that all of the other ones are true. If you know that one of these statements is false for your matrix A, then you know that all of these statements are false. Statement 1, A is invertible. That's true if and only if A is row equivalent to the identity matrix. And that's true if and only if A is expressible as a product of elementary matrices. In other words, if it's possible to write that A is equal to E1 multiplied by E2 multiplied by E3, etc., all of the way up to some endpoint, which we don't know. If it's possible that A is elementary matrix multiplied by elementary matrix followed by multiplied by elementary matrix, etc., then A must be invertible. That's true if and only if A has n pivot positions. And that's true if and only if the linear system AX equal to 0, the homogeneous linear system, has only the trivial solution. And that's true if and only if AX equal to B is consistent for all B. Which is true if and only if AX equal to B has exactly one solution for all B. And the ideas in the next few I haven't taught you yet, so I'm writing them in grey. The columns of A form a linearly independent set. We didn't yet get to the idea of linearly independent sets. The linear transformation from X to AX is 1 to 1. The columns of A span Rn. The linear transformation from X to AX maps Rn onto Rn. 8, 9, 10, 11, we didn't cover the theory yet. Come back and reread these later in the course once I explain what these mean. Number 12, there is an n by n matrix C such that CA is equal to I. Rule number 13, there's an n by n matrix D such that AD is I. And finally, statement number 14, A transpose is an invertible. Either these are true or all of these are false. If A is invertible, then all of these statements are true. If A is singular, then all of these statements must be false. Properties 1, 12, and 13 were these. A is invertible. There is an n by n matrix C such that CA is equal to I. And there's an n by n matrix D such that AD is equal to I. If we know that one of these is true, then the other two must be true as well. That tells us we don't need to prove both that A inverse is the identity and A inverse A is the identity. If we can prove one of these is true, then the other one must also be true. For example, use the invertible matrix theorem to decide if this matrix is invertible. Well, what we can do is we could row reduce this to row echelon form and count how many pivots we have. We can see that A has 3 pivot positions. There's a pivot here, there's a pivot here, and there's a pivot here. Because A is a 3 by 3 matrix with 3 pivot positions, the invertible matrix theorem tells us that A must be invertible. Does this linear system have any non-trivial solutions? We've just seen that this matrix A, the coefficient matrix of this linear system, is invertible. So by the theorem, the linear system AX equal to 0 has only the trivial solution. So the answer is no. There are no non-trivial solutions. Now, in lecture 1, if you can recall, I said that a linear system has either 0 solutions or exactly one solution or infinitely many solutions. There's no other possibilities. Now it's time to prove this theorem. Consider the linear system AX equal to B. Exactly one of the following must be true. Either there's no solutions, or there's one solution, or there's more than one solution. We need to prove that if we're in case C, then AX equal to B has infinitely many solutions. So in other words, we need to prove that if there are two different solutions, then there must be infinitely many solutions. So let's suppose that x1 and x2 are two different solutions to our linear system. So more precisely, we're going to be assuming that ax1 is equal to b, ax2 is equal to b, because x1 and x2 are solutions, and because they're different solutions, we're going to be assuming that x1 is not equal to x2. And then we're going to define a new vector, x0, to be x1 minus x2. And that must be non-zero. Then ax0 is the same as ax1 minus x2, or ax1 minus ax2, or b minus b, or 0. Now, let k be any number. Then I want to calculate a of x1 plus kx0. That's ax1, which we know is b, plus k, ax0, but ax0 is just the 0 vector. So we get b. That means that x1 plus kx0 is a solution of our linear system for any real number k. But then that means our linear system has infinitely many solutions, and we've finished the proof. If A is an invertible n by n matrix, then for each n by 1 matrix B, the linear system AX equal to B has exactly one solution. That was one of the conditions, or one of the statements in the invertible matrix theorem. But this theorem goes slightly further. This theorem says the solution is X is equal to A inverse B. Now, because A of A inverse B is just B, A inverse is just the identity matrix, it's easy to see that A inverse B is a solution of this linear system. So we just need to show that this is the only solution. So let X be any solution of AX equal to B. We need to show that we must have X is equal to A inverse B, because we want to show that A inverse B is the only solution. So we can calculate that AX equal to B, multiply on both sides on the left by A inverse, we get A inverse AX is equal to A inverse B. But on the left, that's just the identity multiplied by X, or X. So we must have X is equal to A inverse B. This is the only solution. Solve this linear system. We can write this as AX equal to B. And this matrix we've looked at earlier. Earlier, we found the inverse of A. So we can use that to solve this linear system. The solution of this linear system must just be A inverse multiplied by B. Multiply this matrix by this vector. I'll leave this for you to check. We get 5, 3, minus 1. That must be the solution to this linear system. The next example is on a slightly different topic. I want to show that it's possible to solve two linear systems at the same time if your coefficient matrix is the same. Now, note on the left of the equal sign that these two linear systems are the same. It's x1 plus 2x2 plus 3x3, 2x1 plus 5x2 plus 3x3, x1 plus 8x3. It's the same on the orange one and on the blue one. The only difference is the numbers on the right of the equal sign. That means we can write down an augmented matrix which includes all of the information. If we imagine crossing out or forgetting about the blue numbers, we have an augmented matrix for the left linear system. Or if we forget about the orange numbers, if we just pretend they're not there, then we have an augmented matrix for the right system. If we use Gauss-Jordan elimination, and as always, I ask you to check this calculation for me, then we get this. Then again, we can forget about one column, forget about the blue column, and we can see the solution to the left linear system. Or we can forget about the orange column, and we can read off the solution to the blue linear system. The solutions must be 1, 0, 1 and 2, 1, minus 1. Let A and B be square matrices of the same size. If AB is invertible, then A and B must also be invertible. Now we've seen this the other way. We've seen that if we multiply two invertible matrices together, then their product is invertible, but this is going the opposite way. We're starting with the knowledge that AB is invertible, and then we're going to use that to show that both A and B are also invertible. So suppose that AB is invertible. The invertible matrix theorem wasn't quite at the start of today's lecture. Told us that if a matrix is invertible, that's true if and only if Bx equal to 0 only has the trivial solution. First, we're going to use this fact to prove that B is invertible, and then after we know that, we'll move on to proving that A is invertible. Suppose that x is a solution to Bx equal to 0. Then we can multiply that equation on the left by A to get AB multiplied by x is equal to A multiplied by Bx is equal to A multiplied by 0 is equal to 0. So x is also a solution of ABx is equal to 0. But AB is invertible. And if we have an invertible matrix, then the only solution is the trivial solution. So that implies that this vector x must be 0. Hence, the trivial solution, x equal to 0, is the only solution to Bx equal to 0. And that then proves that B is invertible. Next, we need to prove that A is invertible. So far, we know that AB and B, and therefore B inverse, are invertible matrices. But A is equal to AI, that's A multiplied by B inverse, or AB multiplied by B inverse. So that's an invertible matrix AB multiplied by an invertible matrix B inverse. And as we know from last week, if we have two invertible matrices and if we multiply them together, we get an invertible matrix. So therefore, that proves that A is also invertible. Diagonal, triangular, and symmetric matrices. Now, before I start, let me just point out, your textbook doesn't have a section which brings all of these ideas together. Instead, these ideas, which we think are important ideas, are spread out through various sections. They're introduced in some exercises, etc. I think it makes sense to introduce these concepts all together because this is something we're going to need later. So instead of expecting you to do the exercises and learn them there, I want to introduce them all together now. First of all, diagonal matrices. A square matrix in which all of the diagonals off the main diagonal are 0 is called a diagonal matrix. There's 4 diagonal matrices in this example. The main diagonal of these numbers, of these matrices, I've put in green. These green entries can be any number that you want. The black numbers must be 0 if you have a diagonal matrix. A general n-di-n diagonal matrix can be written like this. The main diagonal, again, I'm written in green, d1, d2, d3, d4, up to dn. These can be any number that you want, but the other entries must all be 0. Diagonal matrices have some nice properties which make them easy to handle. For example, a diagonal matrix D is invertible if and only if dk is non-zero for each k. In other words, if we do not have a 0 on the main diagonal. And if that's true, then it's easy to write down the inverse because we just take the numbers on the main diagonal and we invert those. 1 over d1, 1 over d2, 1 over d3, etc. on the main diagonal. I'll leave it for you to check what do you get if you multiply d and d inverse together. There's more nice properties of diagonal matrices. The powers are easy to calculate. Again, if D is an n by n diagonal matrix, then d to the power k, all we do is we do each entry on the main diagonal to the power k. d1 to the power k, d2 to the power k, d3 to the power k, etc. So for example, if A is the matrix 1, 0, 0, 0 minus 3, 0, 0, 0, 2, that's a diagonal matrix. We do not have a 0 on the main diagonal. So this matrix must be invertible. And we can write down the inverse quickly. 1 divided by 1 is 1. 1 divided by minus 3 is minus a third. 1 divided by 2 is a half. So very quickly, I could write down A inverse. I can also write down A to the power 5 quickly, because 1 to the power 5 is 1. Minus 3 to the power 5 is minus 243. 2 to the power 5 is 32. And A to the power minus 5 is either the inverse of A5 or it's A inverse multiplied by A inverse multiplied by A inverse multiplied by A inverse multiplied by A inverse. Again, very, very quickly, we could write that down. Another nice property of diagonal matrices is it's easy to calculate the product of 2 matrices if one of them is a diagonal matrix. For example, let's suppose I have a 3 by 3 diagonal matrix and I want to multiply that with some 3 by 4 matrix. Then all we're doing is we're multiplying the first row of A by D1, we're multiplying the second row by D2, and we're multiplying the third row by D3. And if we were multiplied on the right by a diagonal matrix, we have the same idea, except instead of multiplying rows by a number, we're multiplying columns by a number. And that is a nice place to take a break. And let's continue. Triangular matrices. A square matrix in which all the entries below the main diagonal are zero is called upper triangular. On the main diagonal, we can have any number that we want. Above the main diagonal, we can have any number that we want. But below the main diagonal, we need to have zeros. There's also a lower triangular matrix if all of the entries above the main diagonal are zero. And together, if a matrix is either upper triangular or lower triangular, we can just say that it's a triangular matrix. Now, note diagonal matrices are both upper triangular because they have zeros below the main diagonal, and they're also lower triangular because they have zeros above the main diagonal. A square matrix which is in row echelon form is upper triangular because it has zeros below the main diagonal. Upper triangle means we have zeros below the main diagonal. So in other words, we have each entry aij 0 whenever I is strictly greater than j. And for a lower triangular matrix, we need to have zeros above the main diagonal. So we need to have aij is 0 for all I strictly less than j. In this next theorem, I'm using capital L to denote a lower triangular matrix, just some matrix, and I'm using capital U for an upper triangular matrix, any upper triangular matrix. Rule number one, if we take the transpose of a lower triangular matrix, then we get an upper triangular matrix. And if we take the transpose of an upper triangular matrix, then we get a lower triangular matrix. Rule number three, if we have two lower triangular matrices and if we multiply them together, then we get a lower triangular matrix. If we have two upper triangular matrices and we multiply them together, we get an upper triangular matrix. A triangular matrix, just like a diagonal matrix, is invertible if and only if its entries on the main diagonal are all non-zero. The inverse of a lower triangular matrix, if it exists, is lower triangular, and the inverse of an upper triangular matrix, if it exists, is upper triangular. For example, here's two upper triangular matrices. Look at the matrix A first. The entries on the main diagonal, which I've put in green, are 1, 2, and 5. These are all non-zero, so A must be invertible. Now look at B. The entries on the main diagonal are 3, 0, and 1. Because we've got a 0 on the main diagonal, we know that B is not invertible. B is singular. The theorem tells us that A inverse and AB and BA will also be upper triangular. I'll leave it for you to check these calculations. Check that A inverse is this matrix, AB is given here, and BA is given here. These are all upper triangular matrices. A square matrix A is called symmetric if A is equal to A transpose. I've given 3 symmetric matrices here. Now, symmetric means we have some symmetry across the main diagonal. For example, these 2's are the same, these 3's are the same, and these 4's are the same. So if we take the transpose of this matrix, remember that means hold the top left corner, hold the bottom right corner, and flip it around, then the matrix doesn't change. We get exactly the same matrix. In terms of the entries, the matrix capital A is symmetric or symmetrical if and only if Aij is equal to Aji for all I and j. Let A and B be symmetric matrices of the same size. They need to be square matrices, so let's suppose they're both n by n square matrices. And let K be a number. And A transpose is symmetric. A plus B and A minus B are symmetric, and K multiplied by A is symmetric. I'm going to leave these for you to prove. But I want to remark that it's not true in general that the product of 2 symmetric matrices is symmetric. Because the transpose of AB, remember when we take the transpose of AB, we need to swap the orders of B and A before we put a transpose on each of these. We get B transpose, A transpose. As long as B and A are symmetric, B transpose is the same as B and A transpose is the same as A. So we can only have AB transpose is equal to AB if and only if AB is equal to BA. That's important. Let's write that as a theorem. The product of 2 symmetric matrices A and B is symmetric if and only if A and B commute. i.e., it's symmetric if and only if AB is equal to BA. So, for example, note that 1, 2, 2, 3 multiplied by minus 4, 1, 1, 0 is minus 2, 1, minus 5, 2, which is not symmetric. That's symmetric matrix multiplied by a symmetric matrix, but it gives us a matrix which is not symmetric. Or in the second calculation, again, I've got symmetric matrix multiplied by symmetric matrix, 1, 2, 2, 3 multiplied by minus 4, 3, 3, minus 1. That gives us 2, 1, 1, 3, which is symmetric. The theorem tells us that this latter pair, that's this matrix and this matrix, they commute. But the first pair, 1, 2, 2, 3 and minus 4, 1, 1, 0, do not commute because their product is not symmetric. Now, let me remind you, the matrix, this diagonal matrix with entries 1, 2, 0, 3 on the main diagonal is not invertible because it has a 0 on the main diagonal. If A is in an invertible symmetric matrix, then A inverse is symmetric. And the proof is quite simple. If we start by assuming that A is symmetric, then we're starting by assuming that A is equal to A transpose. But because the transpose of A inverse is the same as the inverse of A transpose, and if A transpose is just A, then that's just A inverse. And that then proves that A inverse is symmetric. Let's talk briefly about A transpose and A transpose A. Let's suppose that A is an m by n matrix, and So now A doesn't have to be a square matrix. A could be any matrix. Then A transpose must be n by m. And then when we do the products, A transpose and A transpose A must be square matrices. A transpose will be m by n. A transpose A will be n by n. And let me remind you, when we do the transpose of AB, we get B transpose A transpose. So that means the transpose of A transpose. Remember, we swap these positions of these two matrices. Instead of orange and then green, we need green and then orange. And then we can put transpose on each matrix. So we get A transpose transpose multiplied by A transpose, which is just A transpose. So A transpose, and then take the transpose, we get exactly the same thing. That shows that A transpose is symmetric. And similarly, the transpose of A transpose A is also A transpose A. So A transpose A is also symmetric. A quick example, let's suppose A is the 2 by 3 matrix, 1 minus 2, 4, 3, 0, minus 5. I'm going to leave it for you to check that A transpose A is this matrix. Minus 2 and minus 2, that's a pair. Minus 11 and minus 11, they are the same. And minus 8 and minus 8 are the same. This is a symmetric matrix. And I'll also leave it for you to check that A transpose is 21 minus 17 minus 17, 34. And that's a symmetric matrix. And I want to finish this section by giving one more thing. If A is an invertible matrix, then A transpose and A transpose A are also invertible. A nice simple proof. If A is invertible, then A transpose is also invertible. If we multiply two invertible matrices together, then we get an invertible matrix. And that's all we need to do. That's all I want to say about A transpose and A transpose A for now, but we're going to come back to them later in the course. I'm going to finish today's lesson by talking about some applications of linear algebra. Linear algebra could be used for network analysis. Let's suppose we have some picture like this, some lines and some points where the lines intersect. Each one of these lines are called a branch. And each one of these points where they meet is called a node. Each one of these black circles is a node. Consider a network with 4 nodes in which the flow rate and the direction of flow of certain branches is known. Find the flow rates and the directions of flow in the remaining branches. Well, there's 3 branches here that we don't know the direction of flow and the flow rate. Let's give these letters. Let's call these x1, x2, and x3. And let's just choose a direction for now. If we find that any of these x1, x2, and x3 is a negative number, then we'll know that we've got an arrow in the wrong way. So we can just draw the arrow in the other way. Now, at each node, the flow coming in must be the same as the flow going out. So for example, at node A, we have 30 coming into node A, and we have x1 plus x2 going out of node A. So we must have that x1 plus x2 is equal to 30. Next, look at node B. At node B, we've got x2 plus x3 coming into node B, and then 35 going out of node B. At node C, we can see that x1 plus 15 must be the same as 60. And at node D, x1 plus 15 must be the same as 55. So in other words, we've got a linear system. You know how to solve linear systems. So I'm sure you could find that the solution is x1 is 40, x2 is minus 10, and x3 is 45. One of these is negative. Look, x2 is a negative number. So that tells us that actually the flow is going in the opposite direction along this branch than we've drawn here. Or another example, one I've taken from a textbook. Let's suppose we're looking at a traffic system and we're asked to create a computerized traffic light on this road network. And we need the traffic light to let the correct number of vehicles through so that the average number of vehicles per hour flowing into this road network is the same as the average number of vehicles flowing out of this road network. And then, assuming that the traffic light has been set to balance the total flow in and out of the complex, what can we say about the average number of vehicles per hour that will flow along the streets that border the complex? In other words, can we find x1, x2, x3, and x4 in this diagram? Well, part A is quite easy. We can count how many cars are flowing into this road network. 500 plus 400 plus 600 plus 200 gives 1700. And we can count how many cars are going out of this road network. X plus 700 plus 400. And we want these to be the same. We want the traffic light to let the correct number of vehicles through so that the number is balanced. If we solve these, then we see we must have X is 600 vehicles per hour. Part B asked us to find X1, X2, X3, and X4. If we're looking at each one of these nodes, or each one of these intersections, at A, we have 400 plus 600 coming in, and we've got X1 plus X2 flowing out. At B, there's X2 plus X3 going into the node or into the intersection, and 400 plus X going out, etc. So we have a linear system, and we can solve this linear system. The solution to this linear system is x1 is 700 minus t, x2 is 300 plus t, x3 is 700 minus t, and x4 is equal to t. Now, t is not completely arbitrary here because we can't have a negative number of vehicles driving along the road. We must have a positive number of vehicles on the road. So t must be a positive number, and 700 minus t must also be a positive number. So t must be some number between 0 and 700. And then at the bottom, we can see the possible values of each one of these variables. We could do the same thing for electrical circuits, and I'm not going to give all the details here. I suppose we had a simple electrical circuit like this with currents I1, I2, and I3. We could use the laws of physics to write down a linear system for these three currents, and then we could solve these to find the currents. I'm not going to do this. I'm going to leave this for you to think about. Linear algebra, and particularly linear systems, are also used in chemistry for balancing chemical equations. For example, balance this chemical equation. We have hydrochloric acid plus sodium phosphate gives us phosphoric acid and sodium chloride, which is salt. So in particular, we need to find some natural numbers, x1, x2, x3, and x4, such that x1 multiplied by hydrochloric acid plus x2 multiplied by sodium phosphate gives us x3 multiplied by phosphoric acid plus x4 multiplied by sodium chloride. We need this to be balanced. In other words, we need to have the same number of atoms on each side of this equation. So let's look at each type of atom separately. First, how many hydrogens do we have on the left? We have x1 hydrogens on the left. How many hydrogen atoms do we have on the right? There's 3 x2 hydrogen atoms on the right. Chlorine. There's 1 chlorine multiplied by x1 on the left, and there's 1 chlorine multiplied by x4 on the right. Where the sodium atoms, there's 3 on the left multiplied by x2, and there's 1 on the right multiplied by x4. The phosphorus atoms, 1 on each side, but multiplied by x2 and multiplied by x3. And the oxygen atoms, there's 4 on the left, and there's 4 on the right. 4x2 must be the same as 4x3. So again, we have a linear system. You know how to solve this. I'm sure you could write down that the solution is x1 is x4, x2 is a third x4, x3 is a third x4, and x4 is 3. But remember, we want natural numbers. And in particular, we want the smallest natural numbers which will work. So we're going to choose x4 is equal to 3, and then we have that x1 is 3, x2 is 1, and x3 is 1. An example for mathematics next. Polynomial interpolation. If I have 2 points in an xy plane, then I can find a unique line through them. I can find a unique a0 and a1 such that y is equal to a0 plus a1x passes through these 2 points. If I have 3 points, I can't find a straight line, but I can find a unique quadratic polynomial which passes through them. And if I had 4 points, I find a unique cubic polynomial which passes through them. 4 points means 4 unknowns, a0, a1, a2, and a3. So the degree of the polynomial is going to be 1 less. If there's 4 points, then a polynomial of degree 3. So, for example, we might have a question like this. Find a cubic polynomial whose graph passes through the points 1, 3, 2 minus 2, 3 minus 5, and 4, 0. We're looking for a function y is equal to a0 plus a1x plus a2x squared plus a3x cubed, which passes through these 4 points. Let's look at these 4 points separately. First of all, at the point 1, 3, x is equal to 1, y is equal to 3. So we're going to have 3 is equal to a0 plus a1 multiplied by 1 plus 1a2 plus 1a3. And then we could do exactly the same thing at the other 3 points. At the point 2 minus 2, x is 2 and y is minus 2. So a0 plus a1 2 plus a2 4 plus a3 8 is equal to minus 2, and so on. So again, we have a linear system. This time I've written it as in the form of an augmented matrix. you know how to solve augmented matrices. You know that we should row reduce this. And I'll just give you the answer. We can row reduce this augmented matrix to 1 0 0 0 4 0 1 0 0 3 0 0 1 0 -5 0 0 0 1 1. So of course A0 must be 4, A1 must be 3, A2 must be -5, and A3 must be 1. So the answer to this question is the polynomial which passes through these 4 points, the cubic polynomial, is y is equal to 4 plus 3x minus 5x squared plus x cubed. There's lots more examples about using linear systems in your textbook. Have a look in sections 1.6 and 110. I have one more topic for today. Google. Search engines such as Google also rely on linear algebra, but we haven't quite got enough linear algebra to give the details here. How do search engines know which websites they should put at the top of their listings? The answer is they use linear algebra. After you finish this course, you will be able to understand how at least version 1 of Google's PageRanks works, and that's explained in section 10.2 of your textbook. So sometime in the summer, after you finish this course, when you have a free moment, I recommend you have a look in section 10.2 of your textbook, and at that point you will be able to understand at least how version 1 of Google worked. Next time we're going to move on to talking about determinants, which is a big part of linear algebra. I'll give an introduction. I will explain how to evaluate determinants by row reduction. We'll go through some properties of determinants, and then we'll finish by talking about Cramer's rule. Are there any questions?